So the question is a brain an emergent finite automaton? Alright? And we call it FA. And I asked earlier that we handcrafted, right? Finite automata, we did some example in the class, for example, that accept all the string that contains, say, ABC, right? We also had examples saying that all the strings that end with BCC, right? We had those kind of examples, right? But then, you're smart, and you program it, right? You design it according to task given, then you handcraft FA. So I was asking that, is it possible to let the machine to emerge FA, all right? Emerge FA, and I hope that by the end of the this week we will be able to find out some way of doing it, all right? Emerge in the sense that you don't need to handcraft it, all right? So let's look at the first. We need to extend our definition of FA. It's called agent FA. All right. The agent FA is a four tuple. Right now, before we have this is called S, set of state. All right, S, and it can this first place we can call any. We can use any variable. Right now we use a Q. All right, because the could be S and Q, the same thing. All right. Then you have a sigma. Sigma is the input alphabet, and we can use I or sigma. F is the transition function, and in some textbook use delta, all right? And then we have a starting state, S, all right? And for traditional acceptor FA, we have an F there. F is the set of final state, and now we say agent FA does not need that. I explained to you what we're looking at that, all right? So Q, the same, all right, as before, the set of states, but as output and input. Now, what do you mean by that? All right, so you saw that it is output, you output a state instead of output the accepting or not accepting. All right. And the input means the input state. Right? That's something that I'll explain a little more. All right? Why we need that? Then we have sigma, the same as before, as a standard definition. It's an input alphabet. All right? Then the F is transition function. All right? That maps F, the maps set of state plus input symbol to set of state. All right, just like we had before. And S0 is the same as standard definition. It's initial state. Then we have no F. F used to be a part of the set of state. Now we don't have that, all right? Because the agent FA basically directed output state instead of output, the accepting or not accepting, right? Because acceptor is a special case, so we don't need that, all right? Now, why do we call it agent FA, all right? So let's see what agent is. Agent is something that senses and acts. Something whether it's based on biology or based on silicon, it doesn't matter, all right? It senses and act, all right? We'll give an example that human is aging because you sense, right? You have eye, you have ears, you have skin. You can sense smell, sense taste, right? And you act. How do you act? You walk, right? The muscles in your legs start to contract, and the upper body has to be coordinating, otherwise it fall off, right? Coordinating so you can walk. And when your muscle in the vocal tract start to contract, then you start to talk, right? Yes?
I don't understand what Q is.
Hmm?
I don't understand what Q is.
All right, Q. Q is sometimes we have different letters, and we can use S for set of state, all right? And we have Q. Q is just an S. This is basically a different variables. So is the set of state. Yeah, you write it. Set state. Thank you. Does that help? All right. Thank you. We use different letters, all right? Different letters. All right. Give me an example that's simplest. Agent. Really simple. Not that complex as a human being. Yes?
I like just the Lego robots we work with freshman year.
Robots.
With those guys.
Robots is definitely an agent, right? You have cameras, right? And robot has also touch sensors and has wheels. Wheels are actors, all right? And it has speakers, all right? Speaker on the robot, it can talk, and talking is acting, all right? Simpler. Yes?
Fire alarm?
Fire alarms. Fire alarms, if it has a sensor, it's okay. Just siren won't work. Because siren just have act, right? With noise, but did not have a sensor. Right? Give example that really close to that
Like
one.
smoke detector instead?
Smoke detector, yes, smoke detector, or thermostat. All right, it senses the temperature. All right, if temperature is higher, then it will turn off the heater. Right? If it's too low, lower certain threshold, it turn on the heater. The thermostat is, all right. Fire alarm, yes. Fire alarm, it detects smoke, right, and start to make noise. Right, sense and act. All right, good. So you can see the agent could be very complex and very simple. The reason that in the AI field, it defines agent, so they start to have a more common language. All right, agent does not mean that it has a high intelligence. It does not mean that. All right. Then we talk about the FA agent. We look at the diagram. You see what's going on. All right. So yeah, you need to aim. Because you want to make the letter as visible as possible. If you don't aim, and you can see I cut from here, then the screen is not best. So you want to left or right, you need to aim, all right? Try to make it better. For people see the video, will not see very well. So now, so agent FA, this is our FA, all right? And with memory. And in this case, if FA, sometimes we have state, all right? For other machines, probably more complex. So sense what? That sigma, all right, in the alphabet, all right? And the output, what? In our case, is Q in a set of state. Huh? But I said that this needs to be output 2, all right? So So that has this. That part is new, all right? So this is nothing. It's a big deal, all right? I think it's a very big deal, all right? In other words, that if it's emergent FA, and Q can use that input, all right? And you see that, and you see that why, all right? In our case, it's not, right? In our machine, it's not in sigma only, right? All right. Then we see the limitation, all right? Limitation of all the automata. Right. The automata we had earlier, we just mentioned Turing machine. We did not teach that. And we mentioned the linear bounded machine, LBM. And we also mentioned push-down automata, PDA. All right? We also mentioned FA. So the machine has limitation. The limitation is drawn in a diagram as here. All right? You have physical world. All right? Then somebody give a body specification for you, like human, like robot, like human machine. All right, there's a body, and also a given task. Say, accept all the string that contains ABC, a specific string, right? So that substring is a condition, then you need to accept all the substrings that contain ABC from alphabet. So that one gives to you. That's literally little human being, all right? And human programmer. All right? Then what you do is that you understand the task, all right? You understand you need to do 3 things. First, you start with sensors, all right? You have sensors, maybe one or two, maybe many, all right? For robot, you have many. Then it takes, this is image. Image from a camera, for example, or image on your retina, all right? Then what? Then you do IA, input abstraction. So what do we input abstraction? In our case, right, we say an FA is that accept all the string that contains A, B, C, and what you see here is really A as an image. The A is image. The A is the image, right? Every A is different, all right? Then they say, I don't use this kind of problem. I assume that this one can be many, many different images. It's going to be like this image is this image. But I only take care of that particular A, all right? I only extract a part of it that's relevant to what I'm talking about. Then you have an image with cut off, and over here you have only a sigma. All right, like A. I read A at a time. Next time I read N. All right, that's already abstracted by you or user. All right, a programmer or user. That's going to become sigma. That sigma is symbol. All right, then you also do abstract. You assume that the sigma is restricted. All right. Restricted sigma alphabet. Then you do something that you are really proud of, all right? That's called input-output mapping. Now that's our FA, right? Think about the FA case. And if it's a Turing machine, then you do a little bit more, all right? So what you do is that it's an input, output, mapping. all right? And typically that mapping has memory, all right? In our case, when we've done it, we end up with a table. That table is a memory, all right? And we call it memory M, or machine M, all right? That's what we design. That's what we learn, all right? In the homework, you are also doing that, all right? Then, this one you generate output. The output in our agent FA case is a symbol that's there's a state in a set of state, all right? All right. Then that Q output really does not mean much, right? So you would see the output, then you need to tell the word what does that mean, all right? Then that output you need to be transformed by output abstraction. For robot, if I say Q1 means slow, Q2 means medium speed, Q3 means fast speed, all right? You really need to convert into real value. That value is called image. And why do I call image? Each pixel in that image is for a particular motor, all right? Like steering wheel, so say -3, -2, -1, 0, 1, 2, 3. So you have those discrete values and represented by some Qs. All right, you output Qs, then tell you what heading direction you need. So that's an output instruction. They drive the effector. That effector could be steering wheel, could be gas pedal, right? Could be brake, could be shift, your gears. All right, that's for autonomous driving. For particular program that you probably this one will print out your result. All right, you generate the program result you want. So that's a traditional program, and everybody's doing that. All right, almost everybody. Now I'd like to give another paradigm which is different from that. Because this diagram has a problem, they call it paradigm. Okay, this paradigm has a problem, is a given a task. All right? Do you think your mom, your dad know what you do? You end up with a computer scientist when you were born, and start to cry. You may be a football star, right? How come you end up with computer science? And your parents do not need to know computer science, right? Do you think he knows computer science? At that time, there was no internet, right? Now you know internet, you can teach your parents. So given a task, then you, the program, understand the task. That's a big problem. Big problem. All right? Big problem. Do you think your program was programmed, your brain program was programmed for your parents? Do you think your mother and daddy get into your brain and start to be programmed? No. All right. So let's look at this diagram. All right. This paradigm is new. We say that this diagram says that developmental machines or brains. All right, and it's different from there. All right, let's see what happens. So so your program, it's called given the body. What do we given body? It's a human body example. All right, you have your head, you have legs, you have arms. All right, but without the text. That's a condition. Then it gives to a little guy like you, still programmer, all right? But that program does not do things like input out, and this is the output of abstraction, and RO mapping. This one only do little things. I got it here. Over here there's a DP, right? What's DP? DP is developmental program. Small, really small, all right? In our case, that program just maybe 2 pages, roughly 2 pages, all right? And what does it do? It simulates the function of genomes. Genome has to many other things, all right? Because genome will develop your body. So your body will be different from monkey's body, all right? But we are talking about this mainly for the brain, all right? So that's a small program. And then we cut off, we don't want the RA and OA. We take from directly the sensors, all right? Ooh, it's there. We take images directly, all right? And over here, we send to effector directly. All right? Then in general, this one is one way, and I said that you may need to predict what's the next image. So it's like for primate, all right? For primate, from the brain to your eyes, there's no this route because we have a lot of computation power, all right? It's a high resolution already. But for lower animals like mammals, all right, and cats, it doesn't have this route, all right. Then this one, we have this called X area, all right, X area, and this is Z area, and this one gets in there, output, post direction, all right. So that the effector has both input and output. Then we want to have this one called FA, still remembers FA, right? We want to have emergent finite automaton with memory in that area. This includes the whole thing, right? This is emergent FA, and it has 3 areas, X, Y, Z, all right? X is like your eye, like your skin, all right? And Z is like your muscles, all right? Muscles that you move your arms, move your legs, you breathe, all right? And including your vocal tract, you contract your muscle and start to talk, all right? And Y is in type red. If we assume that this is really emergent FA is a simple model for the brain, all right? Then you have physical work. So compare the difference between the previous version and this one. A lot of difference, all right? The first is that it does not have a task. If you, the programmer, that does the right thing, program this one using, like, for example, this program using, say, Turing machine, or Turing machine, all right? Or Newman computer, then this program is really small. All right, this is really small. But then this itself will not be able to do something like brain does. But it regulates the emergence of the big machine. This machine is emerging, all right? Then if you're considering this is a brain, and that brain is able to take images directly and predict image automatically, and it's also able to generate signals to drive your effectors. And also it takes input from the effectors. Now, this one is already said FA, all right, FA. And people say, hey, FA, so what? FA is a just final state machine. We have a PDA, we have LPA, we have Turing machine. And we think that the FA, even you emerge, means you generate automatically through experience, all right? So living experience, for example. Does that corresponding to brain? If it is, what's the position of Turing machine? Now, still remember at early days, that's last week, we said that Turing machine only does syntax, does not do semantics, right? We already said it at the beginning. So the Turing machine framework has fundamental power. It does not do semantics. And I will submit to you that this one will do semantics and syntax together. And FA seems to me it's sufficient, all right? Because very powerful, very, very powerful, all right? So any questions? All right. And I'll do a characterization of DP, all right, a little bit. DP, developmental program, all right? It's a small program. Right, small program. That's something like a genome program your parents give to you. All right, can be learned on a Turing machine of von Neumann computers. All right, and then you have a generate an emergent FA. That FA go beyond Turing machine. All right, that's my argument that for you to consider. All right. Now, in order to see that how you can immediate FA, all right, then we first have to talk about the how you represent image, and how you represent this image. Then you can get some this one. This one will not be very complex. All right. At the end of this. I think next time we will be able to see how this can emerge, and you judge by yourself does that FA emerge automatically. All right. So let's do that. So let's look at the image first. Image is a matrix. We learned matrix, right? So the matrix, for example, that have 3 rows. 4 columns, right? That's only 12 pixels, all right? So I have numbers like 1.5, 2.7, 10, 0.5, 90, 10.3, 0.1. Those numbers are the intensity numbers of an image. Now the max is 100. Minimum 0, all right? So maximum is 100, minimum is 0. I is doing that actually. I try to normalize the contrast, all right? The contrast so that, for example, if you from indoor to the beach, the light intensity at least increased by 1,000 times, but don't feel much, right? Beach, right? And indoor is also bright, but 1,000 times difference, all right? So our eye is doing that one. So now we normalize to between 0 and 1, then absolute intensity really does not change much, all right? I'm not talking about the really pitch dark night, all right? I'm not talking about that. Then that one we will represent it as a vector, all right? We will represent a vector, all right, like that. All right, so 1.5, 2.7, 10, 0.5, 90, 10.3, 21. All right, so what's the dimension? What's the dimension of this vector? You look at how many pixels we have. How many? How many pixels we have? 12. Yeah, we have 12, all right? So this vector is R12, 12-dimensional image, all right? So we consider small image, but typically for I, you have about 1 million pixels, all right? All right? Actually, more than 1. The upper nerve get out of the eye, it's about 1 million, all right? This reduction at least 100, at least 100, all right? Now, then we talk about how do we match when say image comes in, right? How can you match image with your memory? Now image is represented as vector, right? This is called column a row measure. You one row at a time, all right? One row at a time. Basically, we're like one row, then you line it up. It doesn't matter. This one, it could be this one, this one, as long as you fix. The reason we use this vector is that we can use the notation vector, all right? Now, then we want to say how you can good mismatch. Between an image, say X. We have a very small space, 12 pixels, and a weight vector. We call W, but sometimes they call feature, all right? In the brain, it's a feature vector called W. It's also in the same 12-dimensional space. All right. So now what do we really want? R. There's an X and W. We define this one. Actually, brains are roughly doing that. X make the unit length, and in the product with W. Make unit length, so we make this one, and W we put a circle at the top, means it's a unit vector, right? Unit vector. So the X unit vector equals to X divided by the length, and W is a unit vector. All right. So what the unit vector means? It means that originally your vector. The vector could be very, very long. This is x1, x2, and 3. This vector is really long, original x, right? Very, very long. In beach, this is 1,000 long. And indoor, maybe 1, all right? And we normalize it. We normalize become unit vector, so we have a unit ball. Unit ball. That has radius 1, so that one is x hat. The x hat has a unit length. Right? And it does not care how long that vector is, but only one unit vector. Length is 1. All right. Then the what do we make in the product? All right. So in the product, we have say a vector x, 3-dimensional. In the product with W1, W2, W3. What's in the product? Some of you probably have not learned it. It's learned in a linear algebra. It's called x1 multiplied by y w1 plus x2 w2 plus x3 w3. All right? It's the product and sum, basically. And I'll give you the meaning. What that means, all right? The meaning is that if I have a W. And I have an x hat, all right? And I have an angle between these two. And those are unit vector, right? If they match very well, the angle becomes 0. You match badly, then angle becomes very big, all right? So that R xw equals to, in fact, equals to cosine theta. all right? And that will be taught in linear algebra. The cosine theta is the angle between unit W and unit X vector. Both are vector, all right? So you can see that because cosine theta, then the R of XW is between 0 and 1, right? Cosine theta large value is 1, and the minimum value is -1, right? And when does it become 1? When does the cosine theta goes to 1? Theta equals to what? Theta equals to
0 or 5.
0, yes. 0 or
5.
pi is -1.
Oh, yeah.
Good. So theta is 0, then the x hat and the w hat becomes equal, right? This is a perfect match. So the largest R, the better the match, right? And then if we to say that if the say the mean value where theta equals to, did you tell me? 180 degrees, right? 180 degrees is like that, right? Then the x0 equals to minus, okay, all right? That becomes opposite. So this is really bad match. In the 3D space is the worst match you can have. Opposite. And it gets better, then becomes this is a line, all right? So when we say want to match, well, we want to match that, we will check that number. If that number is close to 1, then perfect match almost. Right? Any questions? So at this point, we say we use the inner product for the two unit vectors as the measure of goodness of match. Do you think Brain does that? Yes. It's the father and you, all right? Brain has a synapse, and the neuron input gets synapse, and the component of synapse is like that inside, all right? And the firing of other neuron is there. And neuron basically doing product like that, and do a summation, all right? Physical, based on physics or biology, what's going on is that this value is the conductance of a synapse, and this is the firing of the neuron that it connects to. And both high means products high. Then we introduce the membrane potential. And all those channels, this is one channel, this is another channel, in many channels, then all channel adds up to the membrane potential. If membrane potential is high enough, we'll fire. Fire means, aha, match well. And I'll get to how you can fire, because you will not be able to fire on its own. The neuron has to compete with us. We'll get to that, all right? So right now, this one inner product is what the brain's doing roughly, all right? If we look at biology, you have a very close formulation that handles that, all right? Any questions so far? I think I have not talked about this length yet, so I'll talk about the length, all right? So x1, x2, x3, it's a constant. If you have three-dimensional, all right, a vector, and what's the length? The Euclidean length is equals to x1 squared plus x2 squared plus x3 squared. Take square root. All right? So this become constant. Then you divide it by this value, means that for each component you divide by this one. All right? You divide by the length, divide by length, divide by length, and you can verify that once you divide by length, means each value, or each component divided by this value, then you end up with unit vector. Unit vector, if you do this, you measure that one, you can prove that this is unit vector. The length is equal to 1. All right? Then realize our desire that origin is very long, then it will become 1. Or very short, it still become 1. All right? All right. Now, I'd like to introduce something that's very controversial, right? A model of the brain, right? I told it in a very important way, without touch too much about biology and the neuroscience, all right? So let's look what the brain is doing. a simplified brain model from the top level. So the brain goes like this, right? Brain is shaped like this, right? Then you have eye, then you have a lens there, then you have a retina there. The retina generates a bunch of nerve that gets into the brain. All right. Normally it goes to brain, right? This area called view area, but don't worry about it. All right. Then for human, it does not have this one, but for other lower animals, they still have that one. Actually predict what's in the air, on the eye, like cat. All right. And then somewhere in the frontal cortex, in the premotor area, is sends signal move down through your spinal cord to muscles. All right. And I draw something that like that. That's your beautiful hand. All right. A beautiful hand, and it has muscles, and the spinal cord has this one, and it goes down there and control the muscle in your hand, right? And then there are parts that go in there, and it should go back there. All right? So two ways here and two ways there, all right? That's a really, really rough model of the brain, all right? And without getting into too much detail. So once you see, you will update your brain, and when you act, now this is very important, right? Everybody, you will see you update brain for sure. But when you act, you also update the brain from this route. You see that? It makes sense, right? You keep playing piano. What happens? Better, better, better. Why it gets better, better, better? Because brain using this route and improve the representation inside the brain. All right? The issue is how, right? Still remember last time we said that in the FA, the state, where is the state? And state, in fact, is in Z. All right. So next, let me see what I've done. All right. Now, the next one, I would say that Z in our previous model Z is the state of the brain, or FA, because we say the FA is the model, all right? And Z is, we have three areas, right? X, Y, Z. So your states in your action, right? Not inside. If it's inside, your mother will not be able to check you. Your mother says, hey, baby, get smarter. Now he can drink the milk. Because the state is in your action, not inside. Right? Not inside, at least that model. Right? Then I will write further our model, all right? The model of our FA. Now remember, we want to enable that FA to emerge automatically without a task, all right? In fact, it will do many, many tasks. So I will say developmental network for DN. There's three areas. X area is like here, all right? Then it has a Y area. Y area is like this is Y, all right? Big Y. Then you have Z. Z is where? Z is your muscle. That's Z. All right. So brain take the image as X, muscles as Z, or motor area, then the entire brain is Y. All right. So now let's see what the Y done. In our FA case, all right, this X will represent sigma, right? You see that the sigma as input, right? And in our FA we have Q, right? State or S, depends on the notation method. So the Q is in the set of states Q, and sigma is in the alphabet, all right? So in other words, that FA will link this sigma with Q, but FA will not have this area. Because FA does not have a brain. All right? FA doesn't have a brain. Does not have the Y area. But we need to change that. All right? So now assume that if we have a 6, 1, 2, 3, 4, 5, 6. You have 6 neurons. They're called X1, X2, X3, X4, X5, X6. All right? So the X is equals to 6 neurons. All right? Then with this one, we have to say 5. 1, 2, 3, 4, 5. Z1, Z2, Z3, Z4, Z5. All right? Now I'm asking, if this was 0, 1 only, all right, 0, 1 only. So I have 5, then 0, 1 only. You have 2 things to do, right? Then I have 5 things to do. So if a binary pattern, you have this many patterns. You have 2 to the 5 binary patterns. And each pattern corresponding to a state. State Q. Now, in other words, that if for FA, if we have many states, say this number, and we can increase this number to 5, all right? And we have very few neurons. For example, you can 2 to the 10, for example. This is a very large number. 2 to the 20, tremendous number. So in the 20 neurons, you can have many patterns. So this is called distributed representation, right? Distributed representation. Each pattern is a state. Before you have to say separate Q to represent a state. Now we have a pattern, all right? It's like FA, now we have vector. Same thing for here, all right? And we have 6 pixels, and how many images you can represent? Many, right? Many. So it's like, well, this one is 2 to the 6 if it's binary images, if it's talk about only binary images. That's a very large number, all right? Instead of individual Q, sigma, all right? Individual input symbols, and you can handle many inputs. In fact, it's not just symbol. You talk about the input images, all right? Then Y goes like this. You have say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right? Then each input will take this input like this. And each will take input from here too. So each input in the Y will have a bottom-up input and top-down input, right? And for example, for this neuron, you have a 1, 2, 3, 4, 5, 6. You have 6 W's: W1, W2, W3, W4, W6. And then for bottom-up input, I write it down, all right? Write it on the. I go over there. Each Y neuron has 2 types of input. The bottom-up input, so response, called pre-response of Y neuron. So you have an input x vector. The x vector. All right? Then you have a weight for bottom up vector. Then you have z. Z is from this area. Z is top down. And it has a weight. It's called top down weight for i's neuron. All right? I equals to y1, y2, y3, 4, 5, 6, 7, 8, 9, 10. Y10. All right? Now this value equals to, as we said earlier, make x univector in the product, make the bottom up weight to be univector. Now this only take care of the inner product of the univector, as we said earlier, right? And this is the bottom up. Turns out that you need not just bottom up. Bottom up you need to check the input sigma is correct, right? But top down, you need to check whether state is correct. So top down input is z, make the univector, and the top down vector make the univector in the product. Right? Now you have two parts. I do summation half. So in other words, that each neuron will take two parts of a match, try to find a match. From the bottom up match and top down match. That corresponding to what? Corresponding to our F, right? F has a state and a sigma. This is a state, this sigma. That will goes to what? Will be to the next state, Q, right? So diagram is the Q, you have sigma, including another Q prime. And this one takes that match of the Q with sigma. Q is from Z, sigma is from X, all right? This is a symbol, now this is a vector. This vector is for sigma, this vector is for Q. All right, this is very important view, all right? Then we do an inner product to find the match. Before when we do this, what we do lookup table, right? Still remember we do lookup table, we have a table, then we have say Q1, Q2, Q3, and we can use S2. And then this is sigma 1, sigma 2. We look up, this is like this one is Q2, for example. Then we find a lookup table. Lookup table is really slow. Over here, we do inner product, do numeric inner product. Then we find a good match, all right? This is a good match. And for neuron, so this is I, this is neuron's I, when I equals to 1, 2, 3, 4. How many neurons we have here? 10, all right? So it goes to 10. Each neuron will compute called pre-response. Then next one I will talk about next time, right? Then what we do is start to find out who is the winner. The winner has the best match. The best match, like you find it in the lookup table. This is called state transition table. All right? So in this case, we do lookup table in the brain. It doesn't do that. Brain does not have a lookup table. So what brain does is that every neuron in the brain, they do the inner product of the two parts, the match of the bottom up and the match of top down, and look at the innate. This is like energy. Pre-response is energy. And as they compete, the winner will fire. Losers will not fire. Right? That I will talk about next time. Any questions at this point? All right. Now, remember, I have one thing, all right? When you write a brain program, you cannot have a government, right?